But Aristotle, he tried to answer it. We'll figure out what he tried. For example, now we will discuss the Aristotle's theory, okay? It was actually a fallacy. Keep that in mind. He tried to answer it, but the theory he gave was completely incorrect. He tried to answer this very question. He said that suppose we have a ground, and over it a ball is laid down. We apply force onto this ball, say a body A. It will be displaced by some distance, okay? But it's a common observation, it's a common sense that with respect to time, at some instant of time, it will come to rest. So velocity will be 0. So Aristotle thought that there is some kind of tiredness. This body gets tired. This body gets tired as the time passes, okay? So he thought that like the human beings, if they work with respect to time, with the passage of time, human body or human beings, they need a rest. They come into rest because they are tired. And similarly, all the objects in the universe, in the physical world, they come to rest because they get tired. It was Aristotle's view, and it was common observation. And at that time, it was well known, and it was famous among all the thinkers of the physical world, which were dealing with these kind of stuff. Okay, we can say physics. But this was a fallacy. He said that the bodies, like human beings, they get tired. So he suggested that every body, if a body is kept in motion, if we want to keep a body in motion, to keep a body in motion, what kind of motion? It's uniform motion. The fallacy comes here, the uniform motion, because I already told you that if the body is in non-uniform motion, then certainly we need a force behind that, because to change velocity we need a push, we need a pull, we need some external agency, which is the force here, to keep accelerating. But in case of the uniform motion, the velocity is kept constant. Aristotle said that as the body gets tired, so we need external force to keep a body in motion. We need an external force to keep the body moving on, okay? So Aristotle gave the theory that an external force is required for every body to keep that body in uniform motion. But that was wrong, completely rejected. That's the Aristotelian fallacy. Look what the fallacy is. This is a fallacy, okay? It was proved that this is a fallacy because now, today, we know that it's completely wrong. Aristotle completely ignored what we today call as the frictional force, but we call that friction. So it was well established for many years, many centuries, I can say, that Aristotle's theory was completely right, because as we know that if any body is set in motion with respect to time, at any instant of time, it comes to a halt, it comes to rest. But it was not because that it is tired, that's why it comes to rest. But the theory, the first person who proved that this is actually a fallacy, it was Galileo Galilei, the founding father of modern physics. Galileo Galilei. What he did, he did some experimentations over this very problem to solve this. He took an object like Aristotle took, but on an inclined plane. This is an inclined plane. A body is set here Okay, he set this body free, and we know under the effect of the gravity, every body which is at some inclination, or at some height, it comes down. Similar effect happens to this very object. This comes down, and he observed that at the initial point, its velocity here, the velocity was 0. But as this body is set free, it comes in motion, and here it comes in acceleration. So velocity changes from 0 to some velocity, say v. Say v is 10 meters per second. Okay, so there is a change in the velocity, and we know the change in the velocity is called as acceleration. Keep that in mind. Acceleration is change in the velocity with respect to time. Okay, or we can represent it for shorter periods of time, for shorter instant of time. It is represented as dv by dt. This is the acceleration. You might be well aware about this relation. So he observed that if the body is set free, it comes in acceleration. Okay, it is accelerated. He did another experiment. In this case, inclination was reversed. He put a body here, okay, at this point. We know it can't climb uphill of its own. We need a push for that. He applied some force onto it, starting with velocity 0. He tried to push it, and it's got at the first instant of time when force is applied, that is at t is equal to 0, its velocity is v. When it is set in motion, before that it was in rest. When force is applied, it comes in motion with a uniform velocity at the first instant. I'm saying at the first instant of time, the velocity is v. Okay, but as it climbs upwards, its velocity gets down, gets decreased. Okay, velocity gets decreased, and it reaches some point. At this point, velocity ultimately dies. Velocity comes to 0. Okay, then he concluded that the body is retarded, because first the velocity was some, say, 10 meters per second, but ultimately it dies out. So there was a kind of retardation which is opposite to the acceleration. So here retardation was observed. The body got retardation. Okay, 2 experiments. One where acceleration is brought into existence. Another experiment, here retardation was observed. Then with the same force, he applied onto an object on a plane which is horizontal. Okay, he applied same force, so the initial velocity here was velocity v. Say for example, here it traveled the distance of 2 meters. Here, say for instance, 2 meters same. But here, when he applied the force here, same force with the same velocity moving first at the first instant, he observed that with the passage of time, as it covers 2 meters, the body does not stop here as in the first case. It goes on and stops here. Why it stops here? There was a real reason behind it, but it doesn't stop here at the 2 meters per second, at the 2 meter distance, which was the case earlier. Okay, it stopped later on after time is equal to say 60 seconds. Fine, traveling a distance of say 50 meters. So he observed that, he concluded that it was not the body which gets tired, because same body was here, same body was here, same body was here. Okay, at the first instant, same body got accelerated. In the second case, it got retarded. So if the body gets tired itself, so why in the first case it get accelerated? Because it is getting more and more energy. As per the Aristotle theory, if it is considered to be true, it should have retarded in this case also, in this case also, and in this case also, but only here retardation is observed fast. Okay, so he concluded that there are three types of motions. One is acceleration, which is the accelerated bodies observed in the accelerated bodies. Second one is retarded bodies, and third one is intermediate. Okay, intermediate. He further tried. He did another experiment. Furthermore, he took a bowl-shaped container and took the same ball here at some height h from the ground level. This is the ground level. At some height h. Okay, he dropped it, but now onwards he kept in mind that this body, the container, is smooth surfaced. That is, he got an idea that the main reason behind that is not the tiredness of the object. It is something dealt with the surface, because here surface was of one kind, here the surface was of another kind, here the surface was of another kind. So he took in consideration the nature of the surface. So for that, what he did, he made this smooth surface as much as possible. So he did an experiment. He dropped this down. It was possessing some velocity. It came here, and ultimately it came almost to the same height. Although there was a difference in height, but approximately we can say this is up to the same height, because he tried to smoothen the surface as much as possible. It is not 100% smooth, frictionless, 100%, no way. So that's why I'm saying that it was approximately h. Say it is h.